All right, good morning, everyone. I'm Professor Kevin Jones, Executive Dean, Science and Engineering at the University of Plymouth and leader of our Cyber Ship Lab, where we're hosting the second pilot for the CyberMar project this morning. We're doing this as a hybrid event, so there are people physically present in the room. There are also people online. So let's just talk about a few basic rules of housekeeping before we move into the detail. First of all, I hope that everybody can successfully see and hear. If we have any problems with video or audio during the presentation, let us know via the chat function and we'll try and correct it. As this is being presented as a webinar, we do have a Q&A option, and at the end of the presentation, we'll have a Q&A session. The way this morning is being organized, there will be a variety of presenters, and when we need to, we will be swapping screens back and forth so you can see the slide deck. The aim today is we're going to present a realistic cyber attack scenario based on a vessel entering one of our partners' ports. So the order for today will be an introduction to the project, an introduction to the capabilities we're using within the project, a walk through the actual scenario from a mariner's perspective to make sure that it's firmly rooted in what we expect in the sector. Then we'll run through the demonstration. We'll take a break at an appropriate point. We will have consequences of this scenario, and then we'll basically go to a Q&A session where you can ask anything that's come up during this morning or anything else you want to know about the project. So on that note, I'll hand over to George, who can introduce the CyberMar project. George.
Thank you, Kevin. Good morning, everyone. Thank you, Kevin, for the introduction. Thank you, the University of Plymouth, for hosting this hybrid event, and thank you, everyone, for participating. I'm Georgios Vassiliou. I'm a senior researcher at the Institute of Communication and Computer Systems, which is the coordinating institute of the CyberMar project. Special thanks for everyone who is connecting to this very important for our project event, which is the second pilot. I will start this event's presentation by providing a short overview of our project. The full name of it is Cyber Preparedness Action for a Holistic Approach and Awareness Raising in the Maritime Logistics Supply Chain. The project has started at September 19, and it has a 3-year duration, although this duration may be extended. It has a total cost of around 7 million, 6 million of which is the EU contribution through the Horizon 2020 program. And as I said, the coordinator is the Institute of Communication and Computer Systems, which is a research institute inside the National Technical University of Athens. The main challenges and the goal that CyberMar projects have now, first of all, it is well known that the maritime information systems in many cases are designed without accounting for the cyber risk. And it's also a fact that digital infrastructures have become essential and critical to the safety and the security of shipping and ports. It is also well known that handling cyber preparedness is a high priority, and it's really important, as it is also important for organizations and companies operating in the maritime domain to be able to estimate in an accurate way, let's say, the cybersecurity investments that they have to do, but that based on a valid risk and econometric models. Having said that, the main goal of the CyberMar project is to unfold in 2 main categories. The first one is to establish a cyber ecosystem for preparing for cyber attacks, and the second one is to estimate the impact of cyber attacks from a financial perspective and support the undertaking of prompt decisions. We have defined 5 main objectives in CyberMar. The first one is to enhance the capabilities of cybersecurity professionals and to raise awareness on cyber risk. And that is going to be achieved through the deployment of the cyber range, through the creation and use of training modules, through the learning management systems, targeting to improve the response times in various resilience metrics. The second objective is to assess cyber risk for operational technologies, without, of course, omitting the information technologies as well. And for that, the maritime cyber risk assessment framework is being deployed and integrated into the CyberMar platform. Another objective is to quantify the economic impact of cyber attacks across different industries with a focus on port destruction. And for that, solutions quantify economic risk in terms of time to recover or product failure at risk are also integrated in our platform. The fourth objective is to promote cyber insurance market maturity in the maritime logistics sectors in a way that the results, although can be adapted to other sectors as well. This has been achieved through the development of recommendations based on the findings and the outcomes of CyberMar pilots and simulations like the one we are having today. And last but not least, the fifth objective is to establish and extend the collaboration and the engagement of CERT and CSERT networks, competent authorities and relevant actors. And our target here is to achieve this through the creation of a maritime NIST community, and through that to engage CSERT and CSERT teams into our project activities. The main concept and methodology to achieve these objectives takes advantage of the cyber range environment and adapts a three-tiered approach. In the first tier, we have people. And for people in the project, what we do is to continue train them through their involvement in pilots, trainings, sessions, and through their familiarization with the CyberMar platform. In the second tier, we have procedures, basically measuring procedures in order to uncover possible areas for improvement and deficiencies in current procedures that followed in the maritime domain. And the last tier is related to technologies, where we want to take advantage of the CyberMar platform capabilities in order to test technologies and to identify possible vulnerabilities in the systems that are used in the domain. So in the context of the project, we have three large pilot scenarios. The first one has already been realized in the Valencia port, and it had to do with simulating the electrical grid of the port, including protocols for protecting the grid and also crisis management after the attack. This pilot has been already completed, and the results are also taken into account into our continuous project activities. The second pilot is the one that we're demonstrating today, and in this scenario is targeted to vessel navigation and automation systems, and the platform will be applied to simulate a ship bridge attack, including attack to navigation and control system. And finally, the third pilot will be related to a SCADA system attack in the port container terminal, especially at the Piraeus port. We will simulate such an attack, but we will also take into consideration possible consequences, cascade effect, extending this attack to the railway operator network. So we're now basically at the third year of the project. Many of the objectives already described more or less have been achieved. Concerning the platform implementation and demonstration, in the consortium follows an incrementally approach for the implementation and demonstration that is divided into three distinct phases. The first one has to do with the initial deployment of the CyberMar Cyber Range and its interconnection with legacy infrastructure. This phase has been completed early in the project, and it has been demonstrated through the first pilot. The second phase is actually being concluded today with the second pilot, and it has to do with the integration of additional high TRL components into the solution, including also the risk assessment framework and elements of the econometric model. And the third phase that will actually start after the second pilot has to do with full integration of all CyberMar components. Also, main achievements have been completed, have been made to the other important training activities of our project. A special section later will describe this achievement. Basically, we have successfully held all level of trainings, including entry, intermediate, and advanced level training, including hands-on experience. So, the platform has been implemented, through which we have offered recently the winter school training session, and also further training is being added to the platform. And a quick note about the expected impacts of our project. We have identified 4 categories. First of all, we believe that our project will have a significant impact on resilience to cyber threats and data privacy breaches. We expect also a significant impact on supply chain efficiency, and also an appropriate investment for cybersecurity. At last, we do think that there will be a significant societal impact through the developed training infrastructures, but also through the standardization efforts that took place in the project context and during the whole duration of the project. So thank you very much for your attention. I really hope that you will enjoy the rest of the presentation, especially the pilot demonstration. It is really interesting. Looking forward also to receive your feedback through the questionnaire that will be later circulated to you. Thank you all, and I now give the floor to Pablo from the Port of Valencia to start presenting the pilot and the pilot story. Thank you.
Good morning. I'm Pablo Jimenez from Fundación Valencia Port. The demonstration that we are going to run today is based on the Port of Valencia, although as you can see, is done in a simulated environment from the CyberShip lab from UOP. The Port of Valencia is the 5th European container port with more than 5.5 million TEUs and almost 500,000 of vehicles. So a disruption of the port will cause a big economic impact. We will see during the following presentations how much could be that impact and how a cyber attack could cause that impact in the port. Now we are going to see the environment, and following we will see the platform that is where CyberMar is based. So now, Kevin.
Thanks, Pablo. So the scenario we've crafted to show you today is one that will basically take advantage of a cyber attack on a large container vessel, and by doing so, block an approach channel to the Port of Valencia. So you'll see that the scenario is broken into a number of different stages. There's how the attack gets on board the ship, so downloading and further propagation of the attack, which is within the IT infrastructure of the sort of the system. We'll then look at how that attack will actually occur on board the ship. So this will be an operational technology attack based on the actual devices that are visible on a ship's bridge and how we would attack that. And then we'll show how that attack would play out in practice. So what the crew would see, what they would be able to do to respond to it, and the consequences thereof. We've made sure that this is very realistic in the sense of the ship operations, including the approach to the port, have been planned out with mariners. The equipment that we're attacking is indeed the equipment that is actually on board the bridge of a ship like the one we're attacking. The The ship we are looking at is actually something that does visit Valencia. So all of this keeps it well within the bounds of reality. And we think that it's a good indication, and so a good opportunity to raise awareness for the sector as a whole of the way a large supply chain based attack could actually result in serious consequences. The vessel we're using is a large container ship, length of 397 meters. This is significant because that length would block the majority of the main entrance to the port. So it also has the capacity to travel at reasonably high speeds, 25 knots. And of course, with that size and weight, actually has mass and momentum that makes it difficult to fix the problem once we've caused it. And again, this is not an unrealistic scenario. This kind of vessel does visit this port. So all of the steps that we've put in to making this attack happen could very well occur in reality. So the mariners within the audience sort of won't be saying, hang on, that couldn't realistically happen. Okay, so having kind of set the overview for what it is we are going to try to do, the next thing we want to do today is to introduce the CyberMart platform and then the details of how that pilot will play out on that platform. Okay, so first thing we're going to do is get an introduction to the CyberMart diateam range. So to do that, we'll pass over to diateam.
Hi, there was also a presentation of the architecture from Emmerich from Naval Group.
Oh, I apologize. Naval Group first. Emmerich, do you want to claim the screen or?
Yep.
Okay, over to you.
You can see. Hi everyone, and good morning to everyone. This presentation speaks about the global architecture of this pilot. This presentation will take less than 5 minutes. As you can see, the CyberMart project is a set of cyber range connect to each other and connect to a specific module. There are 3 of them with specific functionalities. The first is the diateam cyber range. It hosts the simulation and the topology described in the macro model. This cyber range executes the different elements of a scenario we can be used for educational purpose. We can distinguish 3 parts. Let's start with the orchestrator part. It's how to control the running simulation. It's composed by 2 main modules that interact with the platform. The orchestrator is the main controller of the simulation. It can control the other module. It can create any topology and drive any scenario. The LMS, Learning Module System, manages the educational part. The administrator can create online training course, training plan, assign specific course, and track user progress. The second one is the pilot topology. This path simulates all client and server in a port. For example, the mail server and client or all automation available in a port. The last one is dedicated to the monitoring of the topology. The Pred engine concentrates all data of the simulation. The macro framework gives a description of operation risk to evaluate the damage inflicted by the scenarios, and the Econometric model gives the damage caused by a scenario. It's not a real-time module. The CM correlates all security events and gives the status of all machines during the simulation. Now for the Vtt Cyber Range. The IDS, Intrusion Detection System, is a module for detect abnormal or suspicious activity. It can detect and capture evidence of cyber attack for the situational awareness. The SA, or situational awareness module, are used to evaluate a situation for 2 types of students. One for IT or OT specialists, or for high-level profile to raise awareness of the risk incurred by scenarios. And the last is the University of Plymouth Ship Simulator. The cyber range is a set of virtual and physical machines allowing a complete simulation of a boat, you can see. Those parts will be present in more detail during the other presentation. Thank you for your attention. Now Dia team will present the Cyber Range.
Thank you, Emmerich. I'll take over the presentation now. Good morning, everyone. This is Jonathan from Dia team, and I'm going to explain more in detail the platform, Cyber Range, which we're using for the pilot today. As Emmerich just told us, we have several systems connected for the pilots, and so the range we're using is comprised of the three elements. That is Dia team's Cyber Range platform, VTT Cyber Range, and UOP's ship simulator. So I'm going to talk slightly more in detail about the core functionalities which are brought by Dia team's Cyber Range. So our Cyber Range is a virtual environment to realistically simulate cyber systems for various goals, such as combat training, system and network development, testing, or benchmarking. It's been designed and developed by us at the Dia team in Brest, France, since 2002. And we sell this and among other combined systems, industry-leading systems and solutions across the globe. And this is provided to various actors, that is from universities to state services, companies, and cybersecurity teams. And the main focus we have with our platforms is on training in order to reinforce what we call the human firewall. And our rule of thumb is that for a good cybersecurity in any organization, we need to rely on 20% more or less of well-designed equipment and 80% of experienced security experts who know how to use these tools to their full extent. So going back to the actual tools which are deployed today for the pilot in the range. So we have at the heart our Cyber Range platform, which is a multi-user scalable system with a full graphical interface for building and interacting with the simulated network topologies. It also supports hybrid connections, that is to connect elements from the real world, such as hardware equipment or other ranges, into the simulation which is running in the range. It also has a various API for building and controlling simulations, as we'll see later. So just a very quick look at the interface we have for the platform, which allows us to open the topologies that we're going to be interacting with and edit them directly in the user interface, and even go directly into the virtual machines which are running in the simulation. Okay, going back to the tools. Within this Cyber Range, integrated with the main topology tools that we've just seen. The first tool is the Action Manager, which allows us to execute actions inside the machines which are in the simulation. This is independently of the simulated network, so it's completely out of band to keep the simulations realistic. And it also has an API for programmatic control of the actions which are run in the simulation. And this allows us to execute either preparation or scenario actions or any other action you would like to do within your simulation. So this has a web interface that we can see here. So these are all the the machines which are currently active and we can run actions on in the simulation. So we can drill down here and run actions and have immediate return on what is going on. Okay, moving on. We have the Orchestrator and Workflow, as Aymeric mentioned earlier. This is a tool which builds upon the APIs of the core range and also of the Action Manager in order to control the simulation and control the scenario and actions in the scenario. It also allows us to manage what we call hands-on labs, that is supply automatic provisioning of simulations to individuals or teams, and can also be used for trainings or events with integration with learning management systems. And for running the actions, we have a workflow system which handles the administrator customizable action flows. That is complex flows which can be built by the administrator of the platform in order to implement the various exercises or scenarios they wish to. So I'll just show you quickly this tool running. So this is the administrator view. So we have various labs defined in the system currently, and this is the lab we'll be using today. And so we have various signals which can be sent for the different actions, which we'll be using later on. And we have various other elements such as resources which can be supplied for the lab, files, and recurring actions, for example. And we can execute actually right now a signal to send a legitimate email to the into the platform for the scenario. So I can run that right now. Okay, so we can check this, and we can move from here straight to the workflow engine, which is Prefect, which we've integrated with the orchestrator for this. And it's currently running the action that we requested it to. So this is a fairly powerful workflow system, which allows us to run the complex workflows. I want to show you the code which actually implements these. But we have the various actions which are run. And we can see the schematics of the actions in here to allow us to understand what's going on from an administrative point of view. Okay, moving to the next tool. So integrated with the orchestrator, we have a one-click remote viewer, which allows direct access to the virtual machines from the orchestrator web user interface. That is without using the heavyweight clients. It allows users directly to click on links in the orchestrator web interface to access virtual machines. So we can try this right now. So going from our one of the views of the orchestrator dashboard, we can see we have a machine here which is provisioned for me, and I can access this machine directly by clicking on this link. And so I have direct access to this virtual machine, which is of course a fully functional machine, without having to open the full user interface. Of course, we can have any number of machines, and we can run these in parallel, although I only have one link showing right here. This is, of course, extremely useful for training users, so that's its main purpose, to allow the trainees to access their virtual machines. Moving on. Another tool we've integrated with the orchestrator is the VPN Manager. This manages and creates VPN servers on the platform in order to connect the users or other systems into the simulations. We'll see these used during this pilot. So these are level 2 VPNs, so they are essentially wires implemented in the simulation. And so obviously all of the network levels, so IPs address, for example, these are handled by the simulation itself on top of these wires. So the manager itself is integrated into the user interface, so we can easily create servers and manage the servers which are defined. And for example, we can see this server which is currently up and running and is being used to connect our range with UOP's ship simulator, which is currently running. And we have all these other VPNs which are running for VTT's range. So these are, we'll see them later on in the topologies. Okay. Talking of topologies, here we have a view of the topology which has been deployed for this pilot. So we can see the topology of the target organization, which has been targeted on the IT part of this pilot. And so we have the main network, an internet network, an Ssl inspection element, which we'll describe later, some monitoring elements, and the IDS and situational awareness, which was discussed just earlier by Imric, which will be discussed in more detail by my colleagues at VTT in some minutes. And finally, we have the ship simulator, which is connected in order to transfer the NMEA data, which has been transferred into the IDS also. I can show you these in the range itself. And so we have the main topology here. This is a typical Windows-based network with the Active Directory server and various client machines. We have the internet connection at the top. So this is a simulated internet system. So we have simulated a part of the internet, including various web servers and different services, which will maybe have a better explanation later. We also have the Ssl inspection element, which I mentioned. Just a second while it loads. This allows the intrusion detection system to access the content of encrypted web transfers between the clients and the outside world. And finally, have the monitoring segment. Okay, so the monitoring tools obviously start their work by inspecting the traffic which is on the network. And for this, it has access to mirror ports from the various switches in the system, and also, of course, to the decrypted SSL traffic. All of this traffic is sent into this other topology for the monitoring, and so I'll go into this one right now. So this data is collected and sent over the VPN connections we mentioned earlier, and from there it's sent to the IDS system, which is only shown schematically here since it is running in VTT's range. And we also have the various other tools, the SIEM and the prediction engine, which will be discussed in the next presentation. Sorry, in the next presentations. And finally, we have the connection to UOP's range and the NMEA client, which is used in order to request the data from UOP and send it to the IDS via the other VPN. I think that's it for the overview of the topologies. Thank you for your attention, and I'll leave the floor to my colleagues at VTT, I believe.
Thank you, Jonathan.
You're welcome.
Okay, Welcome to all, also on my behalf. So I'm Jukka from Vtt, and I'm presenting the intrusion detection system and the situation awareness modules. So in the CyberMar project, the intrusion detection system and the situation awareness modules are based on the Security Onion, which is a free and open source Linux distribution for intrusion detection and network security monitoring. In this pilot, we use signature-based detection by a tool called Suricata and a network security monitoring tool called Cheek to provide events and alerts about the network traffic, as well as some of the situation awareness tools to present the data to the end users. For example, that could mean the network administrators. CyberMar specific extensions to these components include IDS rules for detecting components of the attack that will take place in the scenario execution, event forwarding from the IDS system to the other CyberMar modules, as well as extensions of the situation awareness dashboards to integrate the outputs from the other CyberMar modules into the situation awareness. That means, for example, the prediction engine that was mentioned before. The intrusion detection system and the situation awareness module, they are running in Vtt Cyber Range, and they are integrated into the two other cyber ranges using VPN connections. The intrusion detection system that is present in the IT part of the scenario network, it is a fairly standard IDS deployment for any organization. There are 3 network probes for capturing and inspecting all the network traffic. These probes are installed in the routers between the different network segments, as Jonathan just shown you. There is the Ssl Inspection proxy that decrypts and inspects all the outgoing HTTPS traffic. And this allows us to also inspect the web traffic that is nowadays commonly encrypted. In the scenario, it is expected that a similar attack has happened before in some other organization, and the indicators of compromise have been shared between the organization, so it's possible to also detect the same threat again now in the future. Because of this, the target organization has signature-based detection rules in place for the specific attack. These rules have been designed to detect a phishing email related to the attack, traffic to an associated website, and then the traffic related to downloading a malicious binary that's then used to launch the attack later on. The intrusion detection in the OT network, that's a more difficult part. So it's not that common that SIP OT networks have intrusion detection systems in place, at least in those kind of systems that are relying on more traditional non-IP based serial data buses. These systems haven't usually been designed security in mind, which makes reasoning about the traffic more difficult. And so it's rather difficult to even implement an IDS system for that kind of traffic. It might be, for example, impossible to verify origin of any message. And also the protocols used in that kind of networks, they are often domain specific. And on the other hand, then most common IDS systems are designed for IP-based networks and internet protocols. In this scenario, SIP's traffic is NMEA-based traffic. It's transport over a TCP connection, which allows us to inspect it using traditional commonly available IDS tools. We have implemented an NMEA dissector for the Cheek tool, and this allows us to log the traffic for future use and inserting it into the situation awareness module. So no actual intrusion detection is performed for this traffic in this scenario. In a real system, anomaly-based detection tools could perhaps be used to detect this kind of attack, but we don't have them present here. Nonetheless, the situation awareness tools, they can be used to inspect the traffic that was logged, and this kind of data could then be used as an example for incident response or forensics actions in combination with other traffic or details that have been captured from the other parts of the system. Okay, this was the intrusion detection part and the situation awareness in brief. And next, I will hand the floor to our colleagues at Atos to tell you more about this CM system.
Thanks, Yuka. Hi, everyone. Well, my name is Jesus Villalobos. Okay, 1 second. I will share my screen now. Okay, so regarding the Ssl CM, we are going to have an overview over it. Well, the Ssl CM is a security information and event management system which performs distributed and near real-time aggregation, dissemination, and processing of events which are received from different data sources or sensors. Then this data received from different data sources are collected in the Ssl CM, and it extracts the relevant information to generate a normalized event. And those normalized events are then correlated based on different correlation rules. The correlation rules in the Ssl CM are written in SPER APL language, which is a high performance and complex event processing system. And this correlation process generates alarms. That is the output of the Ssl CM, the main output. It's worth mentioning that the Ssl CM has a high resilience embedded by design, since it's running in different processes with a topology of processes on Apache Storm, which is a technology developed by Twitter and used by Twitter for a long time. It's a free and open source distributed real-time computation system. So it allows the Ssl CM to have robustness, flexibility, and scalability. Well, in the pilot, the Ssl CM has an important role, and is integrated directly with the IDS as a sensor and the prediction engine, which receives the output, the alarms. So the input of the Ssl CM are the logs received from the IDS sensor. Those logs or raw events are processed in the Ssl CM in the agent subcomponent, where the events are normalized, and the important information is extracted, like the IP addresses, the ports, maybe also the username and password, depends on the data source. In the case of the IDS, mainly those are the IP addresses, ports, and the signature. Then those normalized events are processed in the engine, the correlation engine, where the events are correlated using those correlation rules that we will see an example later. And this process, when the sequence of events is detected under certain conditions with some conditions, then an alarm is generated. And this alarm is then pushed to a RabbitMQ server, which is sent in real time to the prediction engine. So in this slide, we can see an example of a correlation rule. So we give a name, so the user can understand what is happening. In this case, we have a phishing victim detecting downloading malicious file, and for that we defined the APL, the correction rule. It defines the sequence of events and the conditions. In the bottom, we can see an example of a sequence of events that delivers into an alarm. So in this case, that we will see in the example, we have 3 events. That the first one is when it's detected that an email is sent with some malicious domain inside in the body. Then we detect a client that is navigating through this malicious domain, and then we detect that the user is downloading a file that is also related to a phishing campaign. Therefore, we generate the alarm. And this alarm is then sent in real time to the prediction engine that is going to be explained now by my colleague Marcos. So I give the floor to him. Thank you.
The prediction engine aims actually to systematically model past knowledge on attack behavior patterns, to provide real-time predictions concerning vulnerable parts of the infrastructure, and in this way to facilitate educated decisions based on systematized past knowledge and possible risk and economic impact estimations during an ongoing cyber attack. All this inference and information fusion is supposed to be during an ongoing cyber attack. What is our input? We accept input from the IDS sensors, just presented from Yuka, XLCM output events, just presented from Jesus. We take the risk models, the output from the risk assessment models and the econometric models, and we combine them to provide, let's say, a tool for the defender to make some more or less more educated decision during an ongoing cyber attack. So a central notion of the prediction logic and engine is what is an event, what we call an event. It is an open conversation for the entire cybersecurity modeling, let's say, community and endeavors. What should we call an event? We have, according to the data we have received, the experiments we have made, we call an event simply a triple of what an event type and the source and destination subnetworks of the infrastructure this event type refers to. What is an event type? Essentially an alert from the IDS or an alarm or a seed name signature from the CM. Each event is essentially matched to a code word that is a string of characters, and this helps us to encode each sequence of events into a sequence of strings. This slide over here actually shows the overarching idea of the engine. We get the CM and IDS event sequences. We fit a model on this sequence able to predict. This is a variable length Markov model, the general mathematical notion, it's called this way. And we use this model during a cyber attack, receiving real-time event reports to predict what would be the possible next step of the attacker. This prediction is, let's say, presented side by side with an estimation of the risk and the econometric impact of this attack, of this step, if it is successful. An exemplary output of our engine is shown here. You can see, of course, we will also talk about this during the pilot, but more or less you can see that it provides a description of the event, the source, destination, subnetwork. All these are predicted events. The probability of these events that these events are expected to happen, and some information concerning the impact of the possible impact of such an attack step, such an event to the port infrastructure in terms of equivalent downtime, of delays, and of aggregated costs regarding the entire port network. So, thank you for your attention. That was all.
The full consolidation. Next one. All right. I'll just give a brief overview of the capabilities we're using here at the University of Plymouth, and then we'll move on to the actual use of these capabilities in a scenario. So one of the things that we want to be able to do is to make sure that the environment in which we were running is actually fully representative of a genuine ship infrastructure. So one of the things that we have within the lab here is a simulator, but at the physical level, actual devices with which we model the bridge control systems, steering control systems, the throttle, the rudder, etc. And during the scenario, we'll show taking control of those systems to achieve the effect we're aiming to get with the scenario. In order to properly understand and communicate the effect of cyber attacks within the sector, we want to be able to do a risk assessment in a way that is fully appropriate and meaningful within the context of the sector. So we're using the macro cyber risk assessment framework to do both a baseline cyber risk and also illustrate how that risk profile changes for the Port of Valencia due to the activities we're seeing during the cyber attack. MACRA is a very specialized risk framework which takes into account all of the factors that actually apply within the maritime sector. So for a baseline framework, we'd look at the port in normal operation, we'd establish what factors have the biggest effect on their risk profile, and in normal operation then suggest mitigations to those. That changes with a cyber attack. This just gives a very brief overview of all of the tools that we have within the Plymouth ecosystem relating specifically to maritime cyber risk. Today, we're going to be focusing on use of the Cyber Ship Lab to actually effect the scenario, use of the ship simulator to actually give a mariner's perspective on what they would actually be seeing during a cyber attack, and also the macro risk assessment framework, which shows how that risk would vary due to new input gained from the scenario we're running. So with that, I think it's time for us to move to the pilot walkthrough, and I'll hand over to colleagues at VTT and Dia team to talk about the front end aspects of setting up a cyber attack.
Yeah, just 1 second. I'll be right with you.
Just for the audience, we'll be breaking after we've walked through the scenario. So if you can hold your needs for coffee until then, we've got about 30 minutes to go before a break. Is that right?
Okay, can you see my screen?
You can see
Yes.
and hear just fine.
Okay, first I'm going to give a quick recap of the of what's going to go on in the attack. So first, the forces in presence. We have, of course, the center. We have the vessel maintainer, which is the organization which is going to be targeted in order to get the attack on board the ship. So we can hear you, I believe, at Plymouth. Could you mute maybe your microphones? Okay. Right. So as I was saying, we have the central target for the stage of the attack. That is the maintainer of the vessel. That is the Cyber Marine Services company, and whose personnel will be fooling in order to get access to the ship. For this. The attacker is going to send a forged email to the organization, purporting to be coming from their hardware provider, that is North Sea Automation, and telling them about an update to the firmware of the equipment which is installed due to a security vulnerability. In order to gain access to the ship, the attacker wishes to install a specific firmware onto the hardware in the vessel. And so for this, the attacker has faked the official website of the hardware provider in order to provide an incorrect firmware image, which will be transferred to the vessel by the personnel of the maintainer. So in order to do this, there are obviously several stages. First, the attacker needs to do the reconnaissance and weaponization stage. That is finding the compromission vector that they wish to exploit and implement the malicious firmware that they will be sending to the ship. They also need to identify the human targets, which they'll be targeting through the phishing email. And they'll obviously have to clone the website and find a lookalike domain to host the website on, so that the personnel at Cyber Marine Services will not notice that they're going to the wrong website. And also, of course, the email lookalike in order to convince the personnel to use this website. So as I mentioned, during the attack itself, we're going to piggyback on a real vulnerability notification from the organization that is providing the hardware with the malicious email. There is no actual active code in this email. It's simply convincing the user to go to the malicious website. So it links to the clone of the official website of North Sea Automation. From there, the user will download the malicious firmware and transfer it to USB storage for installation on the ship. So they'll need to take the firmware with them onto the ship. So let's do that right now using the tools we've seen in the previous presentation. So if you'll bear with me. So as we've seen before, this is the topology of a Cyber Marine Services organization. And so we have access to the virtual machines of the different users in the organization. So I'll open right now the machine of the targeted individual. Okay. In the meantime, earlier on in the presentations, I showed that we'd sent the legitimate email to the actors in the topology, and so the legitimate email actually we can see here is arrived already, of course, in their mailbox. So as we were saying, we're going to piggyback off this email. So we can assume that the user hasn't quite seen this email yet. And so we'll send the illegitimate email to the personnel. Okay, so send the fake email. So the fake email job is running. Check this in the workflow manager. Okay, so this section is running. We can also see it in the action manager, since the action manager is the one which is used to implement the low-level action. So we have the send fake email action, which is started a few seconds ago. We have some messages here. It's red, but that's not an error. Don't worry, everything's fine. The email was sent successfully, and it should be arriving soon in the mailbox of the target person at Cyber Marine Services. Okay, so the email has just arrived and we have a notification. Let's click on that. And so we can see that in the email that we've received, following the previous email notifying the new firmware update for the PLC that you're using, it's come to their attention that the link in the information was wrong. And so please click here for the correct link. So yeah, this looks fine. It's coming from the proper domain. It looks exactly the same as the emails we normally receive from this organization. And so we can click on the link. So we are now on the website, which is explaining the vulnerability which is found, which is fixed by this firmware. And so the eagle-eyed among you may see that the domain is not the expected domain, but you really have to know that it's there. The actual domain which we should be on is North Sea Automation with an M, and for the attack, the attacker has actually registered North Sea Automation, so with a letter R and letter N, which look very much like an M, especially the small size that the address bar shows. And this means that the attacker has no difficulty obtaining a valid HTTPS certificate for the website, so there's no warning of security issues when accessing the website. From here, the user will probably scan the vulnerability information and decide, yes, indeed, they need to install the latest firmware, and so they will go and download it. From here, they have access to the still the cloned web page for the firmware download, and they will download the firmware. Obviously, since we are on the cloned website, this is where the attacker will substitute the malicious firmware for the proper firmware. So now the firmware has been downloaded to the local machine, and so this firmware obviously is not malicious to the user's system. So there's not going to be any attack on the machine that the user is running right now. But they need to transfer this file to the ship in order to install it on the hardware which is controlling the rudder systems. So for this, they'll be using a USB key. So let's do that right now. So I'll plug this USB key into my machine, and I will send it to the simulation. Okay, so in the graphical interface of our Cyber Range system, we can redirect USB keys to the to each virtual machine as we see fit. So I'll choose the USB disk here, and I will connect it to the virtual machine. Let's see if we have a notification for the USB key. No, we don't have a notification, but it should be there. Ah, yes, we do. Okay, so we'll open the folder. And from there, we can transfer the file to the USB key. It'll take a few seconds. Okay, so the file has been transferred to the USB key that the user has attached to their machine, and they'll be going now to the ship. So we'll eject the USB key. I will detach it from the virtual machine. And as we can see, the USB key is reattached to my host computer, and we have the file that we just transferred. So from now on, I'll be passing the floor back to my colleagues at UOP for the next stages of the scenario. Thank you very much.
Okay, so the first part of the scenario has got us to the situation now where we have a firmware update for the control system of a ship. That firmware update, as Jonathan just demonstrated, now contains a piece of malware. As part of the normal operation of the vessel, we would then expect that that firmware update would be applied as it would be in practice. And we now find ourselves in a position where we actually have erroneous firmware sitting on the ship as it's sort of performing its normal mission. We're going to talk briefly about what the mariners would expect to make sure, again, this is firmly rooted in reality from a mariner's perspective. So I'm going to pass over to Juan, who will talk about what the ship's crew would expect on entering into Port Valencia. So Juan, you ready to talk through that?
Yeah, now following the mariner's perspective to the Port of Valencia. We have here right now the Port of Valencia with a vessel in an inbound pilotage. And right now we follow with the voyage IATA region A. And as we are proceeding with a average winter day, we set the scenario as a 1900 UTC +2 time with the weather conditions of a normal average day of easterly wind with force 2 to 1 to 2 knots. And the high tide is at 2047 local time with a 0.5 meters of height and with a sunset setting at 1912 local time. At this point, we can see the vessel that approaches the pilot station and just arrived. On this next slides, we can see that the vessel has already the pilot on board and proceeds to give the pilot master exchange with the captain. At this moment, consequently, the pilot will take the command of the ship and will start taking the speed of 6 knots, which would be the normal procedures at a slow speed to proceed to the harbor. On the next point, just before the breakwater, the two tags will be attached before the breakwater. One forward with 70 tons bollard pull and one aft with 55 tons bollard pull, and proceeding with 6 knots. On this next point, once arrived to the breakwater, the engines will be stopped and proceeding with a speed decreasing of 5 knots with the tags attached. On the next point, the vessel will slow down at 4 knots with the tags attached and proceeding to use the bow thrusters as the speed is less than 6 knots. On the next point, the vessel already decreases the speed to 2 knots. And finally, the vessel with the help with the tags will finalize with the engines and will secure all lines, making a safe berthing. On the next point, now we will proceed with the same scenario, but simulating that the attack would be triggered. And this will be the same. The vessel will arrive to the pilot station and will proceed with the normal pilot exchange with the captain, and pilot will take the command. And on the next point, he will take the speed of 6 knots as normal procedures, and he will also attach the tag forward and the tag aft. So at this point, the attack will be triggered, and it will cause the ship to have the rudder hard to port and the engine full ahead. The crew actions in this point will be that after 35 seconds, to realize that the ship, they will realize that the ship will be turning to port. And after 40 seconds, they will order the rudder midships, and they will order then the rudder order to starboard. Consequently, after 50 to 55 seconds, they will give the order to stop the engine. On the next point, after 60 seconds, the engine will be ordered to be full astern to proceed to stop the ship. At this point, there will be only 1 minute and 40 seconds to avoid collision. So there is already the ship with momentum turning to port and with 7 knots. At this point, the pilot will also consider to communicate with the tags to proceed to avoid collision. On the last point, the vessel will collide with the pier after 2 minutes and 40 seconds at a speed of grounding out at a speed of 9 knots. In this moment, we can see that the vessel has blocked the entrance, giving a gap of only 900 meters. 100 meters, yeah, meters gap. And then they will give to the, at this point, with the tags, they could only avoid to break this collision with the pilot if they only have the time to communicate that they will do it after 60 seconds since the beginning. They will have only, after they communicated after 1 minute, they will have the time to react of 1 minute and 40 seconds. Therefore, there is little time to react, and the ship will be already with a speed of 7 knots and with momentum turning to port. In addition, the tag operators will not expect this to turn to port, as it will further on and enter in the harbor. Then the tag operators will not avoid crashing the ship. In the best scenario, and the tag operators responded perfectly, they could slow down the turn, crashing the ship with the side of the vessel rather than the bow. And other considerations will be dropping the anchor, which will not give enough time to the anchor to hold and stop the ship. In conclusion, the entrance will still be blocked. On the last slide, we can see an example, and the salvage operations will be estimated to be of 3 to 7 days. And this will depend if the ship is whole, and they need to make sure the vessel does not take water once moved. And if it needs to be pulled, as shown in this example, 8 tugs will need to be needed for the size of this vessel, which will require the transit of the other capacity of the tugs. Other considerations will be if the vessel can be floated off by dropping ballast water to load and unload in situ. In this occasion, the tide will have a minimum consideration as we are in the Mediterranean. Additional actions will be to remove substract from the vessel with dredge pumps and air lifts before tug operations. This may require dive teams, will suppose a significant amount of work. Therefore, in conclusion, 3 to 7 days will be a realistic as shown in the Suez Canal.
Okay.
I will now hand over to
Thanks, Juan. So a lot of detail in that, but one of the things we wanted to make very clear was we've thought about this from an actual mariner's operation. Everything has been planned out as it would be in a normal scenario. We've run it with crews in simulation, and basically from that point, this is pretty much an unavoidable attack. What we'll do now is show how the simulation setup, both the physical twin and the ship simulator for the mission, will play out to sort of so you can see it in practice. And if we have time at the end, maybe we'll show it in a full bridge version so you can see what the crew will see. I think for those of you who are mariners, this will be a somewhat worrying scenario, and looking at it play out will probably make it very real to you. So Wes, can we run the demonstration? And we have to share the right screens, I suppose. Yeah. Okay, so what you're seeing now, obviously, is the view sort of from the bridge of the ship, looking out the window as we're entering the Port of Valencia. That's sort of a simulated view run on a ship simulator. Bottom left is basically the instrumentation as the crew is seeing it, and to the right there's the charting view, which you can see at the bottom left of that. The ship is approaching the port as Juan said it would be according to normal operation. For the sake of simplicity in this demonstration, we haven't attached tags. We could do so, but it's just clearer if you see the ship moving. I think we've already proved that attaching tags doesn't actually make any difference to the consequence of the attack. Okay. Right. So the vessel is approaching as planned. The crew is seeing normal behavior. We have malware installed on the rudder and throttle control systems of this ship by the mechanism we talked about earlier. We have that malware set up so that it's basically geo-triggered. When on its chart, it enters a particular latitude-longitude combination, which happens to represent the point that Juan indicated as where we would trigger the attack. The malware then changes the packets that are being sent via the NMEA protocol across the internal network. So instead of the packets that would represent the commands as input by the crew, what we actually get are packets that are sent by the malware, which, as was said earlier, basically caused a full rudder lock and a full throttle when the crew was signaling rudder amidships, reverse thrust, and so on.
So, okay, I might speak to some.
Yeah,
so we can.
Yeah, we'll run it a little bit faster than normal because, of course, a ship moving at 6 knots going into a port the size of Valencia, it would take a little while. So basically, we're speeding up the time sequence. So what you were seeing is the ship entering port. You will see at some point that there is unexpected behavior. We play this out in a full bridge simulator with a real crew who aren't expecting anything particular to happen. What then happens is there's the few seconds of panic when they realize something is not quite right. The few more seconds of trying to work out what they should do. They're trying desperately to do the right thing, all within that about 1.5 minute window they've got before the collision becomes inevitable. Okay. So the ship is now proceeding with the entrance to the port.
No.
Yeah.
Yes.
Okay. So now we're instigating the attack. In practice, this would be, there are packets going along to the control system which identify the position of the ship. The position of the ship now corresponds to the triggering point. The malware running on the system, which we are showing on the cyber console at the back of the room, is now changing the packets. So the control system, both rudder and throttle, are getting erroneous messages. What we will now see is that the rudder will change angle, the speed will change, accelerating when the crew are indicating slow down. And what you can see on the screen, still it takes a little bit of time, ships don't move that quickly. So there's another view which is sort of showing within our environment the physical representation of throttle and rudder, because as I said, we want to make sure that in reality, this indeed could happen. So we have the control systems in the lab. Obviously, for some reason, they wouldn't let us bring a real ship in here to show it happening. And also the Port of Valencia would be very unhappy if we did it for real. So we want to show the physical effect of the control system interference. So you can see the rudder is on full lock. You can see the throttle has resulted in the propeller spinning very quickly, which is not what you normally want on dead slow. And now we're beginning to see that the ship is veering to port when the crew are indicating that they actually want rudder amidships to enter the harbor properly. So the collision is now developing. By this point in time, in practice, the crew is saying, something's not right. This is not right. Why are we turning to port? We actually have the rudder amidships. Why are we speeding up? We have the throttle sort of set at halt. The crew will now be sort of going through the thought process of what do we do? They will, of course, be trying to adjust the controls. It makes no difference what they do because they no longer have any control that reaches rudder or throttle. The malware in the control system is basically not forwarding any packets and is generating the constant full throttle, full rudder lock. We're now getting much closer to the breakwater. I would imagine that in practice, the mariners amongst you now are feeling very uncomfortable about the world, and people are physically moving up and down the ship. And you see that the ship is now firmly on a collision course to the breakwater. By this point, given the mass of the vessel, even with tugs pulling, even with dropping an anchor, there is literally nothing the crew can do to prevent this collision. And then we see the inevitability played out. The roughly 400-meter vessel has hit the breakwater, and so will either be grounded or even more dramatically hauled. At that point, the ship is basically blocking almost the entire entryway to the port. Therefore, traffic in and out of the port over the next roughly 1 week is going to be close to zero. There isn't much opportunity, particularly for large vessels, to be able to get in and out with the deep water channel blocked. So the scenario is played to completion. This is where we would end up at the end of the scenario. Okay, and actually those of us in the room can hear that the throttle is still running full on regardless of what sort of the crew are doing. So that basically is a scenario that could happen at the Port of Valencia. So I think the next step now is we will hand over to colleagues at VTT to talk about what could be seen during this entire scenario and how we could gain awareness and perhaps take some mitigating action.
Okay, thank you. Let me share my screen. Can you see my screen now?
Yes.
Okay, thank you. So if we use the LMS system to go to the situation awareness and the IDS machine, we can open it here. It should open soonish. So this view here shows the events and alerts that the IDS system has generated based on the signature-based detection rules. We can see here some events that correspond to the attack scenario that Jonathan described. For example, here we can see an event about possibly malicious content in an email. If we look into the event more closely, we can see that this rule is about detecting the malicious domain in the email content. So it has detected that there is an email that contains this crafted double-squatted domain. The other alarms are about the user's traffic to the malicious web page. So when the user clicked the link, there has been DNS queries to that, considering that web page that the IDS system has detected, and then of course the HTTP traffic from the browser to that web page. Also, finally, the IDS system has detected when the malicious firmware file was downloaded and also generated an event about that one. So this is detected from the actual network traffic. All of these alerts that it generated, they were also passed to the other components, so the CM and the prediction engine modules that were described earlier. Okay, then if you go to another view that shows more about the data that has been collected, we can see that there have been lots of events during the pilot execution. This number of logs actually means that there have been 150,000 or so logged individual events during the execution. And as the execution took about 20 minutes. This is quite much. There are lots of information extracted by the IDS system about different protocols that were used within the network. So all the network segments, for example, the DNS queries, there has been SSL traffic, some servers or clients have asked for new addresses using DHCP. So most of this traffic is actually describing the normal network activity in the target network, but it also, of course, describes the attack itself. If we go here to the network intrusion detection tab, we can see the same events here that we had in the other view. And we can see that there are lots of information extracted also about the attacks. So we have, for example, the addresses from where the suspicious traffic originated from and where it has gone, the port numbers, about the protocols that were used. And so this is basically a very good source for information, for example, for incident response, that what has happened in the network. Then if we go to look at the NMA information, we can see that this traffic was captured during the attack from the ship's OT network. It has been imported into the same dashboard with the rest of the data from the IT network. We have, because of the dissector that we had for this traffic, we have extracted a lot of information about the actual content of the traffic in the ship network. So we can, for example, see that there have been different types of NMA messages flowing through the network, with what kind of messages there have been. And that can give us an idea that what kind of communication there is, and if there's something wrong, for example, some component communicating too much or something like that. We can also extract information. For example, here we have extracted information from the NMA messages that contain the GPS position of the ship. And so we have this kind of situation information also available that can be extracted from the traffic. So we can see that it's somewhere near the port that this has happened. We can also, for example, see the control values that were communicated during the execution in the ship network. And we can here see, for example, the change of the value that took place during the attack. We had a slight problem with capturing the traffic, so we don't have all of the kind of normal traffic before this, but this is basically the point in time where the attack happens. And that kind of information could then be used if we had a correct type of intrusion detection system in place, then it could maybe be used for intrusion detection, but also in trying to investigate what have happened later on. Okay, then we also have the prediction engine output described in this same dashboard. Let's take a bit smaller time frame so that we can see the information better. I guess that was just about the attack time. So this is now describing what the prediction engine has predicted about the traffic in the IT network. And would Markus want to comment on this output?
Yes, let's go a bit, let's scroll down a little bit. Let me explain the columns because actually this is our output. All the rest are some fine visualization made by Yuka. This table is the output of the prediction agent. It is evident far left column is actually the timestamp of the prediction. The next is a batch ID that, let's say, gives a unique ID to the prediction. And when we say prediction, we mean actually the predicted event that is about to happen. The description of the event, for example, we see that we expect a malicious domain traffic, and this actually is a prediction coming from the CM, which is the next the next column. The following two columns essentially refer to the subnetwork between which this traffic is detected, this event is detected. The source is the clients for this at least event, the first event we see here, and the destination is somewhere outward. And then the following columns essentially give, let's say, estimations on the lowest and the highest probability this event is expected to happen. For this malicious domain traffic, we see that is quite low. It's about 7%. This means, and the samples, which are, let's say, the samples low and the samples high, are the corresponding samples based on which this calculation has been carried out. The more the samples have, the more, let's say, sure we are and confident we are about the prediction. Let's say, to give the defender some slack of making his own decisions, we have decided to provide, let's say, a lower and a higher bound on the probability estimate. Can we go a little bit right? To the next columns.
You want to?
Yeah, to the next, just to explain. Okay, the following columns are actually refer to the fusion, let's say, of the prediction with corresponding outputs from the risk assessment and econometric impact assessment models. Average count, okay, delayed count actually says that if the destination subnetwork of the predicted event actually gets affected, what kind of delays, how many vessels are we expecting to be delayed? What kind of, yes, how many vessels? How much delay is expected for each vessel? And an equivalent downtime, what this means for the port. And the last three columns are essentially aggregated cost estimations, lower bounds, mean value, and upper bound of what does this mean for the port of Valencia. Essentially, this is why you see actually the same number. The same numbers in its row, because each event refers to the port of Valencia. The econometric model provides this information at the level of ports. For this let's say experiment, the corresponding lower bound, upper bound, and mean value are essentially the same. Okay, that's all from my side.
Okay, and that was what we have from detection. So let's continue with the other presentations.
Okay, so I think where we are in the proceedings now is we've established that the ship scenario has played out. We now have a ship blocking the port of Valencia. So we'll take a 10-minute break, and at the end of that break, we'll come back and we'll look at the follow-on consequences. What will be the cost of such a cyber attack, and what effect will it have longer term? So according to my clock, it is either 9 or 10:47, depending where you're sitting. So should we say we'll be back at on the hour? That gives us just about a 10-minute break. So back on the hour, and we'll continue with the second part of the pilot. Thanks, everybody. All right, we're back at 11, so hopefully everyone is back. And we are recording again. Okay, so where we've got to now is we know what the attack did. We're now going to look into the consequences of that attack. So the next presenter is Camille from University of Plymouth. He's going to talk a little bit about the effect on port throughput and how we modeled that in some of our simulation. Camille.
Where's the keyboard?
Kimberly ran off with it.
Thanks. So as Kevin has stated, I'd like to talk about the resultant impact on port throughput if the scenario that we just looked at before the big materializes. So I'd like to discuss three main things. One is what do we see normal port performance, and how the port will perform during the periods when that disruption happened and during the periods immediately after those after that period. Then I'm going to talk a bit about the recovery time, which is basically the time it will take for port performance to get back to its normal levels. Then I'm going to talk about the delays that we faced at the port, which is the difference between the ship turnaround times you see normally and the ship turnaround times that you're seeing now, because the vessels can go in and like queuing for long periods of time outside whilst the vessel is being dislodged. So those are three main things I want to talk about. I want to talk about what that means to the port operations. Then after this, then our partners are going to continue and talk about the wider supply chain impacts. So just quickly looking at the broad aims, we've got three broad aims that we want to cover here. The first one, we want to estimate the relative impact that the cyber attack would have on port operations, as stated. Then I would then like to talk about, for the scenarios of concern, I'll talk about the estimates of the consequential level of that port disruption, or in other words, how port performance would be affected by that disruption occurring. Then I'd like to provide delay estimates or delay information that we use to inform the risk modeling and econometric modeling process. So the delays that are produced by the port throughput exercises feed into other tasks within the project, so most notably the econometric side, and that's used to then estimate or identify wider supply chain losses. So the key input sources that we'd use to conduct this work, the three main ones, which is port traffic information, which is basically information pertaining to the traffic that the port normally sees. So how many vessels come in a particular period of time, the average turnaround time, normally number of berths they have, number of cranes they have operating, information such as that. So traffic information and information on assets used at the port. So most notably, crane assets, but also both key cranes and yard cranes as well. So, and another important source is obviously the cyber scenario under consideration, because that then tells us how long the disruption will be for. In this case, we know from the scenario that we just looked at there that the vessel would take that alternative path and block that channel for 3 to 7 days, so mean around 5 days. So that information is important. It's one of the key informations that are used as input to the port throughput estimation code. So talking about impact. So in order to estimate the level of disruption a certain scenario would have on a maritime port, we use a combination of expert assessment, as like just saw with the period of time it would take for that vessel to be dislodged and taken out. That was estimated by expert assessment. So experts, mariners, basically helped us come up with those estimates, helped us come up with that input that we use in the port throughput simulation. Then we have historical information on the port. We know how many vessels go in, as I said before, ship turnaround time, parameters such as that. Then you use that information in the simulation to come up with delay estimates. So given all that information, given the scenario, given the expert assessments, given the ITOT assets available, the cranes, and given the scenario in question, that information, you can take that and use it for these exercises. So we use these discrete event simulations of port operations to achieve these purposes. So on the right here, I've got a flow chart of the basic flow of this exercise. So basically you have scenario specification, then you have information on the port, you have information on a ship, you create the model with that. Then combining those, you know what happened in the scenario, you know specification of the port, you compute the impacts of that on the port and on ITOT, on the assets first. The assets will become unavailable for some time. Then you use that information to compute the impact on the port or vessel. Then after that, then that can be taken even further downstream, and you can look at the supply chain. So here I've got just an overview of the key physical port operations you'd see on the port. So basically, you'd have ship arrival, ship with berth, you'd have that, you'd have cranes unload that, you'd have interport transport, you'd have that then go into the yard. Then you have the opposite route, so going from the yard that way. Then you also have the land-based transport going out to the hinterland, so you also have the trains and trucks. So you have the key, you have transport past the container yard, and you have transport going out. And three main flows we have containers going in, import, containers going out, and some being transshipped just going in the container yard and coming back at another period of time. So these are physical processes. Then in addition, we have some support processes, which are usually supported by some, usually by IT. So you have, the port will do many things. It will do berth schedule plans. It will do, there'll be data exchange. There'll be planning of the yard and actions such as these. So these ones aren't physical processes, but these are processes which are undertaken by the port to support port operations. So they might use terminal planning softwares and the like, hosted on conventional IT equipment. So you have here the physical ones first here, then here is the support ones here. So here I'm going to the first point, the impact on port operations, normal versus impacted. We're going to look at a couple of indicators here, but a handful of indicators of port performance. The one is the number of vessels waiting to berth, so the queues outside, how that looks. Then we're going to look at the ship turnaround time, how that changes, normal versus disrupted. Then you're going to look at the port delays, which is just the difference between the normal ship turnaround times and the ship turnaround times that you experience during those periods of delays. So looking at the vessel queue length, the results from analysis show that you can expect the queues to really shoot up, because with the scenario you have complete blockage of the channel, so you can't have vessels going in, you can't have vessels going out, so all those vessels now start to queue outside there. So you have this huge spike you see on the graph there of the vessels queuing there, that even when the vessel is dislodged and taken away, you don't recover immediately. As you see there, the recovery is quite gradual, because you can't service all those vessels instantaneously and just bring the queue down very quickly. It will go down slowly over time. So approximately you have a disruption that spans a lot higher than the direct delay. Similarly with ship turnaround times will spike up. They'll take a long time to come down. And you'd have recovery times being very high. So you'd have, like here, you have many vessels being delayed, and the average delay being 2.4. That's for the mid-estimate. So ship turnaround time has gone up from 1 day to around 3.5. So you have quite significant impacts to port operations if you had an incident such as the one that we looked at here. So this last slide. So due to the fact that one of the key tasks of the port is to facilitate cargo processing, basically facilitate the unloading, loading, and transport and storage of the cargo, it's very important that the port keeps running efficiently. So as we have shown, if ships are delayed, if ship turnaround times are up and ships aren't services, those delays could have wide-ranging consequences of the port, which would take quite a long time to resolve. And if that disruption is severe enough, it could also affect the wider supply chain. So I would hand over to our partners at AIR, who will be looking at the downstream effects of this, so looking at how this would affect the supply chain. Good
morning, everyone. Thank you, Kennedy. Can you hear me well?
Yes.
Okay, so I'm just going to share my screen. Okay. Hopefully you can see my screen now.
Yeah, it's all good.
Thanks. So I'll be talking over the next 10 minutes or so. I'll be talking about the econometric modeling framework and the results that, as I'll show in a second, build on the results from the macro model. And as you can see here on this slide, our econometric model framework is based on 5 key modules. I'll go through each of these in a bit more detail, but just as a start, I can give you a brief overview. So the first step for us is to define essentially how different products and raw materials actually feed into the production of different industrial products. Once we understand that, we use that information and combine with trade data to define what we call our supply chain network for different industries across a variety of countries, as I'll show you later. The next step would be to calculate the disruption to, in this case, to the port, which is, of course, in our case, is given by the macro model in terms of the disruption in the number of days to the port operations. We'll then, the econometric model will then propagates this disruption through the nodes of the supply chain model, and then we compute the corresponding losses to the different industries at different countries. So let me explain all of this in a bit more detail. So in terms of the first step, which is where we define what we call the product dependency. So this is where we enumerate and define the sort of like the interlinks between the physical parts, such as raw materials or basic and intermediary products that are required to construct any given final product by a given industry. So this is what I'm illustrating with this schematic on the left, where you can see the progression from small products or raw materials on the left, all the way into the final products on the right. And you can see that along the way, there's many different interlinks between the different raw materials and intermediate products that feed into one another. Another important step is to understanding and establishing the actual correlations of products and semi-finished products and raw materials across different industries, because some of these products will, of course, feed and be used by different industries for the production of different products. So we also take this very important step into understanding all these correlations. In terms of the products that we support and we analyze, those are the first category, let's say, the first level of differentiation of these products is shown here. So we have 32 different product categories, ranging from crop and animal production to several types of manufactured products. These are defined in terms of the NACE taxonomy, which is the European taxonomy for different products and industries. This is just what we call level 1 differentiation, but we can actually go further in terms of the breakdown of, for instance, let's say if we look at manufacture of textiles, there's going to be different subcategories here that we can account for. So once we have understood this, essentially these product dependencies, we start building our global supply chain network model, which is where we combine our view of the product dependencies, with what we call our product dependency models, with several sources of global trade data between countries and within countries as well, to map out this global supply chain. So a very simple example here that I'm showing here in this illustration is, let's say that if the product / industry that we're thinking of is Germany automobile, we see that there's several different intermediate steps or products or semi-products that feed into what eventually will be the final production of automobiles in Germany. So this spans from electrical components in Austria, metal forming in Switzerland, semiconductors in Japan, and so on and so forth. So this is, of course, a very simplified example, but just the objective here is to give you a sort of an overview of what kind of global supply chain model we are developing. So the next step would be to identify in what nodes in this network would suffer some disruption. So, I mean, in the case of today's scenario, we're talking about disruption to the Port of Valencia. But the objective here is to then propagate this initial disruption through the nodes of the supply chain. And as I mentioned before, the this initial disruption in this case is provided and estimated by the macro model and is then propagated through the affected nodes in the network. So again, just to give you a very simple example, looking at the Germany automobile industry, if let's say that we, in addition to disruption to the port of Valencia, we also have a disruption in Japan semiconductors, and they both, these disruptions would both feed into the final disruption to the production of automobiles in Germany. But I mean, this could be any in terms of the modeling capabilities, it could be any number of disruptions to any number of nodes. So again, in the case of today, what the results I'm going to show you are the results corresponding to the propagation of the initial disruption to operations in the Port of Valencia. So once we do propagate this disruption, eventually what we're going to do is estimate what we call the downtime, so the time in which industrial operations are not possible due to these supply chain disruptions, and we determine the economic losses as a function of this downtime in days and the daily revenue for the product group slash industry slash country of interest. So the results I'm going to show you in the next slides are something like along the lines of total loss in revenue for, let's say, the automotive industry in Germany. And of course, this could be for another type of industry in another country as a result of the initial disruption to, in this case, the Port of Valencia. So in terms of the economic impact to, in this case, to the EU and plus the UK region, what we have estimated as a result of the initial disruption estimated by the macro model, which was given in terms of this range of possible values of 3 days, 5 days, and 7 days, which you see here on the table on the right. See that the top 6 countries in terms of loss to total industrial output are France, Germany, Italy, Netherlands, and Spain. And this is also exemplified here on the bar chart on the left. And perhaps not surprisingly, the most affected country is Spain, because this is where the port is located. But then given all the interconnections between trade between all these different countries, we also see quite a significant impact in France and in Germany and Italy and the UK. So just to give you a general sense of the type of losses we're talking about here. So for Spain, which is the most affected country, we're talking about a range of losses between 2.5 and almost 6 billion euros. In Germany, which is the second most affected country, we're talking about a range of losses between 1 billion and 2.4 billion. So these are quite significant losses as a result of the initial disruption to this specific port and essentially the disruption to the supply chain as a result of that. If we then look in more detail into Spain and Germany, which are the top 2 most affected countries, and look in more detail into the industries that are affected within that country, we see that in case of Spain, the 3 most affected industries are manufacturing of transportation equipment, food manufacturing, and also chemical manufacturing, with also quite a significant proportion of machinery manufacturing being significantly affected as well. If we then look into Germany, we see there are essentially four to five main affected industries. So food manufacturing, again, chemical manufacturing as well, as in the case of Spain, machinery manufacturing, and also electrical equipment, appliance and component manufacturing. And again, it's, such as the case of Spain, also transportation equipment manufacturing has been significantly significantly affected. So just to wrap up, and this is my final slide, I just want to give you sort of some additional insight into what these results can provide. So far in these slides, I've been talking about absolute total loss in terms of revenue to these different industries in a given country. What I have not showed yet is essentially what that loss in a given country corresponds to in terms of the proportion to the total economic output of industrial output in that country. So that's what I'm showing here as a percentage. And again, not surprisingly, Spain is the most affected one with a percentage of close to 2%. Then the remaining countries sort of range between 0.2 and 0.4 to 0.6%. But then one country that stands out here is Portugal, which we really didn't think as very significant from a total loss point of view, given the difference in total industrial revenue and how it compares to countries like Spain and Germany and UK. However, in relative terms, we see that actually it has a very significant expected loss. And this is, again, not surprising given the close links in trade between Portugal and Spain. So with this, I'll end my presentation. So I'm going to stop sharing my screen and pass it along back to our colleagues in Plymouth.
Okay, thanks for that. And I believe the next presenter is WMU.
Yes, thank you. I'll share the screen, just a minute. Thank you all. Can you hear me? And do you see the slide?
Yes, we can
Yes,
see
we can
Anthony.
Thank you.
Want to make it full screen though.
I cannot. Otherwise, I lose the Zoom interface. I don't know why. I'm Vtt Agostini. I'm on behalf of Monica Canepa from World Maritime University. I'm presenting to you the training and awareness raising part of this project. The main task are the familiarization and training with Cyber Range platform, the formulation of cyber training packages with a focus on hands-on and practical training, exploring new awareness methods and qualification track, and training activities and synergies with European agencies or other cybersecurity financed projects. Let's see a bit of in details the expected output in this project for those areas of focus. We are committed to provide at least 2 physical training per experience level, with 3 levels of training, with at least 50 unique trainees, and at least 2 massive open online courses per experience levels, plus 2 capture the flag. Well, capture the flag is a form of gamification of the learning of cybersecurity that is organized as a challenge, a suite of challenges, technical challenges that allow to train both defenders and attackers on cybersecurity activities. We see here a visualization of the 3 levels of trainings we taught. We have an entry level that is more on the form of a cyber awareness at large training, open to different participants from different field of knowledge. And then we have intermediate and advanced level with that are more focused on hands-on activities and on advanced topics on cybersecurity, and that will make use of the cyber range and lesson learned from the pilots that are treated in this project. So we see that you have 2 entry level, 1 more technical, and 1 more focus on managing cybersecurity. We have 4 intermediate level trainings focused on the cyber range usage, and the last one is focused on the Valencia port scenario. Could you please mute your microphone? Thank you. And then we have 5 advanced courses, practically are all hands-on, and we have in the A005 training the lesson learned about the vessel pilot, and this is the pilot that we are seeing today. Here we have the depiction of the different target groups that are addressed with the trainings. So we try to cover all the interest parties in the maritime sector, even the seafarers. So some, especially the cyber, the entry level trainings are addressed also to seafarers. We see here a calendar of the already implemented action and the future action. With on the right part of the slide, we have the list of all the trainings. So we already delivered almost all the trainings, and we have left the capture the flag. Just a word about the train the trainers. That is a we have seen before here. The train the trainers is a special course held by DIA team that developed the cyber range, and has been dedicated to the people that will have to manage the cyber range from the point of view of creating the scenario for learning activities. Here we have a depiction of the results obtained in terms of reaching of these trainings. It's referred to the trainings of the intermediate level held last December. We see here that the audience is coming from all over the world for all these trainings, and we have to keep in mind that those are intermediate level trainings, so they require some pre-knowledge to be fully exploited. Here we see the detail of the national composition. I know that there's very little the writing in this slide, but we have people from Colombia, from Algeria, from the United States, from the Netherlands, so really all over the world. And here we see the results, statistics about a training organized last February, which covered advanced level trainings. It has been a joint project, a joint activity with another EU financed project, Foresight project, that is treating a similar subject. Those trainings have been administered through the learning manager system that we have seen this morning, early this morning, in the overall architecture. So allowing the participant to interact with the cyber range and with the scenario created the cyber range for the learning activities. For the participation to these trainings, participants will be required to pass a certain threshold in a questionnaire, in a technical questionnaire, in order to guarantee that other participants that all the participating were able to fully exploit the contents of these trainings. After the trainings, we evaluate, we ask the participants to evaluate the quality and the characteristics of the trainings. And here we have the results, some of the results about the advanced 002 training. We see that we score well about organization and about the ability to gain knowledge applicable to the work. About the development of the LMS platform, thanks to the collaboration with the other team that developed the LMS integration with the Cyber Range, and lately agreed to develop also a model integration so that we will have the ability to connect with different learning management system. We have been already able to serve some of the trainings through the LMS platform. And last week we finished to introduce in the platform the contents also of the trainings already held before the LMS was ready. And we are planning to add the remaining training to material to this platform. We see here a depiction of the appearance of the platform. So for the development of novel approaches and awareness methods, we are exploring the idea to use the capture the flag, and also we are we have already mapped the training with a scheme for cybersecurity qualification that is the NICE of the NIST, National Institute of the Standard of Technology. Those are some results from the evaluation test needed that we require the participants to fulfill before and after the fruition of the training. The questionnaire is the same before and after, and is taught in order to measure the increase in the knowledge, skills, and abilities of the participants. So we see the situation before and after. So we see that the median points is increased of 1 point. And for I004 trainings, it's remaining the same in the average for overall, but in the detail, one can see that it's improved in some fields. Concerning the synergies with EU agencies and other cybersecurity projects, we proceeded mapping the existing EU project to liaise with, and agreed with the Foresight project to hold joint webinar and the joint training that has been named Winter School and has been held last January. With a participation of 56 people. And during this winter school, we had as keynote speakers representative from the Maritime Safety Division of the International Maritime Organization, the chairman of the European Coast Guard Functional Forum Cybersecurity Working Group, a representative of the ENISA, So we tried to keep together all the main actors on this subject. The next activities will be the next training, the first in-person training session that we are able to do because due to COVID-19, you know, a lot of activities has been held only in online. So we will have an in-person training in Genoa at the Ssl facility, and we choose based on cost on local stakeholder interest a selection of entry-level trainings. So we will have the collaboration of the University of Plymouth, and we will treat mainly entry-level cybersecurity subjects. Next action are deploying the learning management system, better deploy the learning management system, and plan for the next training, especially for the capture the flag. Thank you for your attention. If you have any question, please ask. I will be very happy to answer to you.
Yeah. Okay, so the final piece of the day is Q&A. We have questions within the Q&A session. So I'm happy to coordinate the Q&A. We have some people live in the room here, and as you know, we have others online. So the first question as asked is, will the presentations and recording of this event be accessible on some server? George, do you know the answer to that?
Yes, the presentations will be shortly available through our website. And also, I believe that the recording of this pilot will also be available. And I want to take this opportunity and invite all of you to follow our project, visit our project site, also follow us in social media, and see our project activities back to follow. So we want your feedback, and we want you to follow us and see what we do.
Okay. The question. Yeah, we have a few more questions.
Where's the question?
Evaluation.
Remember what slide it was on?
What are you looking for?
The questionnaire.
Oh yeah, yeah. So I think very important to mention that, just in case people drop off before we actually finish, we do have a questionnaire that we'd really like to get your feedback on this event. And okay, that'll do. Yeah. So hopefully you're going to see on the screen the final slide, which will be in the slide deck when you see it. We're very interested in getting feedback. We're interested in evaluation of how today went. You can see on the screen that there is a link to a web form where you can provide that feedback. That would be very helpful. It would allow us to work on sort of further development and also sort of help direct the remaining piece of the project.
That is correct, yes. Very valuable feedback that we received in order to, and in the view of the upcoming activities and the third pilot, to enhance whatever we can and to include this feedback. Do we have more questions?
And I think we saw some other questions. Kimberly, can you kind of basically read them out and we'll work out who's going to answer them?
Yep. So a question I have for the panel is, how do you kind of, how do you think the future work will be extending after this?
Oh, I mean about the simulation, about the
Yes, and
simulation.
any aspects of today, what do you kind of see future work building on this game?
Do you want me to start? So from the point of view of sort of the maritime specific technology that we've seen today, I think we've shown that being able to run a simulation where sort of the capability of a ship is looked at directly has been very useful to the sector and has helped sort of integrate with the cybersecurity technology that we've seen in other parts. I think as we move forward, more integrated technology, so ships, ports, rail, control systems within the environment will again be this sort of combination of classic cybersecurity technology for the IT side, specialist technology for the OT side. So, I mean, from our point of view, extending our capability into ports and into other parts of the transportation ecosystem is something I think would be very useful. I don't know if anyone else wants to sort of comment on future directions based on their technology.
Next question.
Yeah, indeed. The team, of course, will be continuing to develop our platform and the various tools. In particular, the Orchestrator is going to be continued to be developed in order to support training activities for the rest of the project, and also in the future to allow more effective training of personnel in the use of cybersecurity systems and also just for cybersecurity training in general. And of course, we continue working on our core platform.
Okay, we've had one more question in the Q&A. So the question says there are IACS ship registries which grant cybersecurity additional notation to ships implementing their guidelines. Have you ever checked those, and in your experience, are those guidelines granting an acceptable level of security? I can make a first comment. I mean, we have looked at all of the current security guidelines and operational practices, ranging from sort of IMO regulation through BIMCO guidelines, through to sort of other organizations that have offered guidelines and sort of directives. The truth is, they are, of course, better than nothing, but they are still very much at a sort of fairly basic level. So I think that they would provide an acceptable level of security against collateral threats, very little security against specific threats.
And if I may add, in the context of the project, we're working on providing standards and guidelines in accordance to, in collaboration with European organizations to try to propose standards for this domain.
Next question.
Next question. So we have a technical question saying, as we've seen different cyber ranges connected today, what is the average delay between the cyber attack and the IDS detection?
I assume that's a question for VTT or Jonathan. Or Jonathan, yeah.
Yeah, the VPN connections are real time, and so the transfer of the data, so the capture of the network data from the range and its transfer to the VTT's range for analysis is essentially instantaneous. And so the only short delay would be in the IDS system, which is quite quick, especially for the rules, as it needs to run them in real time. Jukka, if you want to expand on that.
Yeah, as Jonathan said, the detection itself after the traffic has been received by the IDS, it should be quite instantaneous. Although there is then a small delay before any of the alerts or the events end up into the dashboards in the situation awareness. And of course, for the VPN connections and the traffic forwarding between the ranges, today we saw quite small amount of traffic also, so it might be that there's some more delay if there is lot of traffic that's forwarded into the IDS.
Yeah, there are two different elements to see. Yeah. So the IDS itself in the real world, in a real organization, would be deployed within the organization typically, so you wouldn't have any delay due to the VPN. But of course, yeah, even the delay in the IDS is on the order of a few seconds. I would say no more. Obviously, for the in the case currently where we have the interconnection between the VPNs, if there's a lot of traffic, there could be some buffering involved, but that is easily solved by using appropriate, let's say, data links for the scenario which has been run. At least in our case today, the data rates were definitely low enough to have completely real-time transfer. So way less than a second of delay.
Also thinking about the distribution of the components, it would be possible to distribute the IDS system also between the ranges, so that, for example, the detection parts would be so that there are detection probes in all of the ranges, and that minimizes the traffic between the detection point and then the situational awareness modules, for example. So this kind of technical measures can be used to cope with possible problems with the delays for the IDS system.
I assume you're giving a visual answer to the question, Jonathan.
Yeah, you should be seeing my screen.
Yeah. Yes.
Mm-hmm. And so in the range, we could definitely set probes directly on the mirror ports of the switches, so that the large amount of traffic would be analyzed directly within the core range, and then the data would only be the alerts and events which were captured from the network traffic would be the ones which would be sent across the VPNs in order to limit the amount of traffic that needs to be transferred. So that would also allow running a similar scenario, but with much more traffic, even on low data rate VPNs.
Okay, do we have more questions?
We have a couple more. The next one is, given these pilots kind of merge cybersecurity and maritime, are both sectors fairly willing to kind of accept these scenarios and pilots on both ends?
I mean, let me answer from the mariner perspective. One of the reasons we've worked so hard to make sure that procedures and practices do actually comply with real world practices is because basically we want to make sure the sector does accept that these are realistic scenarios, because without that, we run the risk of not being listened to in the right way. So speaking from the mariner side, the scenarios are very realistic.
Yeah, I agree. And I believe when they actually see through the simulation, they actually understand, because the awareness is in a low degree. Yeah? So I believe through this kind of simulation, people see that.
Yeah, and if we have time at the end of the Q&A, we'll do a walk down the corridor and we'll show you what the mariners see when we do these things. Anybody else want to comment on that? No? Any other questions?
Do we want to do the next one on my list? Do you want to try and tackle this one?
Well, this one was actually asked in chat, which was, what about checking the hash of the firmware before installing it on the vessel? Do vendors play the game? The answer to that is it depends a lot. These days, many shipping companies have policies of basically doing a virus scan on any plugged in USB devices. So to that level, sort of malicious USB sticks would be caught. For this particular scenario, as the question asker clearly understands, the firmware is not malware as far as the USB detection would take place. Not all manufacturers would have a hash on the firmware in order to be able to check it before installation. The other thing is, it's not terribly difficult for us in the malware to fake an equivalent hash. So the chances are the most sophisticated companies might catch that installation. The vast majority wouldn't. It literally is a case of, I've been told to download, I've downloaded, I plug it in and I install it. Sometimes from a USB stick, sometimes from a laptop. So I think it would be caught in some circumstances, not in the vast majority.
We have another question on the importance of training experts, both in maritime, but also IT security in maritime. Any thoughts on that?
Well, training is actually the basic for everything. You have to keep training in order to get better. So this through this training, the simulation, the actual training assessment we provide, we hope that we target to so that mariners or people involved in the whole supply chain, maritime supply chain, could be better aware and better trained in order what to expect and how to react in such situations. So if all get better, we think we can mitigate such attacks.
Okay, shall we stop the Q&A there?
Yes.
You can maybe give some closing remarks and I'll see if I can set up my corridor walk.
Yes, I want to thank all of you for participating. First of all, I want to thank Professor Jones and the team here in Plymouth, in the University of Plymouth, for hosting this event and for their organization efforts and their efforts in the pilot execution. I also want to thank all involved partners for their work for today's pilot. I really hope that you find this demonstration interesting. And as I said before, I want to invite all of you to follow us in social media to see what our next activities are. And we want you there to provide valuable feedback, and also to remind you once more and ask you to kindly follow the link provided also through the chat and follow and complete this evaluation questionnaire. Thanks again, everyone, and hope to see you in a future project activity.
We'd like to give you a quick sort of tour of what we had here, and particularly go down to the simulator so you can see what this scenario looks like from Mariner's point of view. So you've already seen in the background sort of the cyber ship lab. This is sort of the console end of the lab where we do configure and where we can set up our cyber attacks. I'm giving Juan time to set up the simulator. This is actually what we call the vault, which is the equipment room where basically we can set up any sort of bridge system with collections of real world equipment wired together in an appropriate way. At the other end of the corridor, we've got what we call our full mission simulator, which is where we've actually played out this scenario with a number of different crews, ranging from cadets through to experienced mariners. And it's been quite interesting to see the reaction from the mariner community rather, when basically we do a cyber attack. So this is our full ship's bridge simulator. And this basically is what you will see when we are sort of looking at it from a sort of a simulation point of view, this is the entrance to the Port of Valencia. So this is the simulated mission entering Valencia. I'll move to the back of the room and we'll let Juan actually go near the steering. Right. So what the crew will be seeing as they enter the port is basically, full wraparound representation, accurate model of the port, accurate model of the vessel. As we sort of saw in the earlier simulation, things progress very slowly for a while. We're moving towards the port. We'll see at some point that the malware will be triggered, the control of the ship would be subsumed by the malware, and just as we saw earlier in the lab simulator, this would then be crashed into the breakwater. So I just wanted to give you an impression of what this looks like in practice to a mariner, because it's very disturbing for the mariner when they find they've lost control of the ship in this environment. And it's much more easy to appreciate what that looks like when you see it in this kind of setting rather than in the lab. So just wanted to share that with you before we left. I'll stop sharing here now, and I think that will wrap up the day unless there are any final questions. So thanks everybody, your attendance and contribution, much appreciated by all.